Thanks. All right, so today, I kind of have modest ambitions for today. I think I mentioned in the first talk that there's this theorem that Mike Hopkins, Matt Ando, and myself proved that there exists a map of commutative S algebras from the Borism spectrum called M string to TMF, topological modular forms. I'm not really going to talk about this theorem very much today, or especially about its proof. I may say something at the end. We'll see. Before this theorem was proved, there was previous work by Ando, Hopkins, and Strickland on orientations of this sort. And the theory of power operations for Marva-E theory that I described in last week, or when I've been describing for the last 2 lectures, was constructed in order to solve this kind of problem. So these techniques weren't enough to sort of produce this map, but I think it's instructive to sort of see how this works. So that's what I want to talk about. So just to say what they did, they made there's the following little picture you draw. So what is this M string? It's, well, I can write a similar picture where I replace M with B. So I have BSO B spin, and spin, the infinite spin group, has a characteristic class, and the homotopy fiber of that is a space that we call B string. And, well, we can sort of backtrack and look at complex groups. So we have BU, a complementary tower, BU, BSU, and a gadget which doesn't seem to have a fancy name, BU6. And then they're associated diagram of Borism spectra for all of these of the same shape. And so what they did is they did the slightly more restricted problem of constructing MU6 orientations. So they showed here, maybe it has 2 parts. One, every complex so every elliptic spectrum. So remember, I defined elliptic spectrum in my first talk. It's an even periodic ring spectrum together with a elliptic curve defined over the coefficient ring of the cohomology theory, and together with an isomorphism between the formal group of the theory and the formal completion of the curve. So I would have written it something like E C over pi 0 V, and then some isomorphism. Every elliptic spectrum has a canonical MU6 orientation. So that's a ring homomorphism from MU6 to E. That's a ring homomorphism in the classical sense, homotopy map of homotopy commutative rings. And then I can refine this to what's called an H-infinity ring. So this term H-infinity ring, I don't think I've mentioned it in my talks, but it's shown up in the recitation. An H-infinity ring is sort of I'll say a little bit about this later. It's sort of what you see if you have a commutative S algebra and you only look at what that gives you in the homotopy category. So I'll just use this statement now, and then I'll come back to it later. So they show that if E is an H-infinity ring spectrum, H-infinity elliptic spectrum, which is K2 local, then there exists a canonical H-infinity orientation. See, E. So it's given by an H-infinity. And you can actually say a little bit more than this. But
is the claim the map from 1? I mean, these are both maps in the homotopy.
So
the map from 1 is H-infinity?
Yeah. So it says, so I need to make sure, and the E has to have the right kind of structure. And if it does, so it's the same map. I should say that. You're absolutely right. In the case when you're in this setting, we've actually refined the map we found here to 1 here. Okay. And all of these structures are related to the Witten genus, which at least in their papers conjecturally is a map from from M string to any elliptic spectrum. All right, so that's sort of what they do. What?
That last thing in the data for an elliptic spectrum, you've got alpha mapping GC to what?
What's GC? GE.
Okay.
To C hat, the formal completion of the elliptic curve at the identity. All right. So what I want to do is I just want to give some idea of what goes into this. So I'm going to start very basic. So let's backtrack a little bit. So let's start with an even periodic ring spectrum. So it's complex orientable. No commutative S algebra or anything yet, just a homotopy commutative ring. So of course, this means it's complex orientable. So we could pick a coordinate and then write the cohomology of BU1 as a power series ring. There's a choice by using the choice x of coordinate. Okay. And a coordinate determines an Euler class for line bundles. So if I have a line bundle over x, then I get an associated Euler class defined using the coordinate x, which lives in the E cohomology of x. Well, it depends on x and it depends on L, so I'll write this as x of L. That's the Euler class. And what is this explicitly? Well, this is really the thing you get by taking the map that classifies the line bundle. So remember, L is classified by a map from x to BU1. That induces a map in cohomology, and then you just see where this chosen coordinate gets sent, and that's the Euler class. All right. So of course, tautologically, if I compute the x Euler class of the universal line bundle over BU1, that's just x. And associated to all this stuff, as probably everybody knows, is a formal group law. So if I've chosen a coordinate, we get a formal group law, x1 plus over f x2 in the power series ring on 2 variables. And we have the formula that the Euler class of a tensor product of line bundles is the formal sum of the Euler classes. And this notation has the feature that the f here really depends on x. I ought to sort of put it in somehow. It depends on the coordinate. So up till now, and probably further on, I've been talking about formal groups, which are a coordinate independent way of talking about formal group laws. All right. So let's consider the following space, BV. It's the disjoint union of the classifying spaces of the unitary groups. This is the classifying space for complex vector bundles. So a homotopy class of maps of x into BV is exactly an equivalence class of complex vector bundles. So if I have a complex-oriented theory, in particular, let me make an observation. This space has some structure. For instance, it's an H-space. An H-space in several ways. In particular, it's an H-space under a map which classifies Whitney sum. So there's an H-space structure. Whitney sum of vector bundles. Of course, Whitney sum of vector bundles is an operation on the category of vector bundles, and the category of vector bundles over a space is a symmetric monoidal category under direct sum. The space that represents that structure doesn't just carry an H-space structure; it carries an E-infinity structure. So this map is the underlying H-space structure. This underlies an E infinity space structure on BV that encodes direct sum. But just using the H space structure, this means that the E homology of BV is a ring under the Pontryagin product. And we can say what that ring is. This is well known. This is E0. It's join an infinite list of polynomial variables, which I'll call BK. Just to get things specified, so what are the BKs? Well, the BKs all live in the homology of BU1, which maps. No. This is an E infinity space, but it's not an infinite loop space. It's a commutative monoid in some sense, but it's not a group. And this ring is just a polynomial ring. Oh, so this is the map induced by, if you like, the map that classifies the universal line bundle. And this object, the homology BU1, is a free module on a list of elements that are called beta Ks. This is a free E0 module. What are the BKs? Well, those are classes that it's a basis for the homology that's dual to the monomial basis for the cohomology, which is a power series ring in X, which you can't quite see it up there. So these are dual basis, monomial basis of a power series ring. It's not really a basis of the power series ring. You have to look at the finite approximations, the CPNs, to read off the correct answer here. So of course, just to note here, these also depend on X. I should have a little X in here too. Okay. Now I want to consider F. F is going to be a spectrum. It's E smash the suspension spectrum of BV. So of course, this is the spectrum whose homotopy groups are the homology of BV. Since E is assumed to be a homotopy commutative ring spectrum and BV is a homotopy commutative H space, this is also a homotopy commutative ring spectrum. It's also even periodic. So this is an even periodic ring. Sorry, yes, even periodic ring. Right. Okay. What I'm going to do in a bit is describe how power operations act on this ring in the case where E is Moravia E3. That's what I'm headed towards. Why do I want to do that? Well, that's going to be relevant for the argument of Ando, Hopkins, Strickland. They're not working directly with BV, but rather with some of its friends. Those are its friends. So, and it has and there are other friends I didn't list there. All right. But I want to do the calculation of level of BV because it's a little bit easier to keep track of what's going on in this case. Okay. So this ring spectrum F is interesting because it comes with a kind of canonical characteristic class. In fact, a tautological characteristic class for vector bundles. Tautological. So if I have a vector bundle over X, I'm going to get a tautological class, which I'll call angle brackets of V, and that lives in the F cohomology of X. Goodness, what is this tautological characteristic class? It's the tautological thing, because I built F using BV, which is a space that classifies vector bundles. So here's what I do. I take my vector bundle, I classify it by a map from X to the classifying space for vector bundles. I'll make those spectra by taking suspension spectrum. But, well, this has a ring spectrum map to E smash sigma infinity plus BV using the unit for E, the identity element in the ring. So that's V angle brackets. So it's a tautological characteristic class it's using. And it comes with one property, which is the following. If I take the angle brackets of a direct sum of two vector bundles, what's that going to be? Tautologically, it's going to be the product of the angle brackets of the individual bundles, because that product is computed using this operation on BV. So this is kind of a universal example of a characteristic class of vector bundles. Not virtual vector bundles, vector bundles that has this kind of multiplicative, that property for Whitney sum. I haven't gotten much sleep lately, so I may, if I veer into incoherence, let me know. I'll try to take a quick nap and recover. All right. I know there's a, yeah. All right. Let's consider an example of such a thing. So there's the universal line bundle. Well, there's a corresponding characteristic class of this sort, angle brackets L univ, which lives in the F cohomology of BU1. I can calculate what this is in terms of a coordinate. So if I pick a coordinate, this is the sum bkx to the k. I won't do that calculation. Everybody can do that calculation. It's a tautology. Remember, the b's also depend on x. So the right-hand side of this equation depends on x as it's written. But no matter which x you use, you get the same answer, namely the left-hand side. So this is a canonical element. X, by the way, is the image of in F0BU1 of the one from E, because there's a map from E to F. I'm going to call this thing gamma sub univ. And I'm going to interpret it as the universal example of a function on the formal group of E. This is the universal example of a function on G, the, no, I want to say G, G sub E, formal group of E. Right. What am I doing? Oh, goodness. Let me spell that out. So it's the universal example of a function. So here's the idea. So suppose I give myself a ring homomorphism. So when I have a ring homomorphism, I get to take the formal group that's defined over E and move it over to a formal group defined over R, phi per star of GE. And if I also give myself an element gamma inside the ring of functions on phi per star of GE, so that's sort of non-canonically some kind of power series ring over R, then given this and this, then there exists a unique ring homomorphism from the coefficient ring of F to R, extending phi and such that, well, if I take F upper 0 of BU1, which is really E upper 0 of BU1 tensored up to F, and I have to decorate this. When I base change formal groups, I can't just tensor up their rings. I'm really tensoring up the underlying ring of scalars. So I have to write it like that. There's a completed tensor product. And I get this ring along phi, and this sends, well, this thing contains this universal, purported universal function, and this homomorphism is going to send this thing to the given function gamma. In other words, ring homomorphisms from F0 to R, which extend the given one from E0, correspond to functions on the formal group defined over the ring R. Right. And if you like, that's a calculation from the fact that I can always expand gamma as that power series where the coefficients are just free variables. Right. So in fact, you can even write down, what this does in coordinates. It sends, well, let me not do that. Let me make one more remark. There's another piece of structure on the space BV, which is a diagonal map. And so this gives F0, which is the E homology of BV, the structure of a Hopf algebra. So it's not merely a ring, it has a co-multiplication, Hopf algebra. So the coproduct represents an operation on functions. The coproduct, delta star, represents the operation on functions, which is multiplication. That's a calculation you do by calculating what the coproduct does on, say, elements BK, which is a straightforward exercise that I won't do. All right. Now, one more fact. So I have this universal characteristic class that lives in F0. So I think I said already, well, I didn't say this. I said for the universal bundle, if I have any line bundle, then I get this class, brackets L, which is inside F0 of X. If I compute what this is, I can compute this in terms of brackets of the universal line bundle, which is the universal function. So this is, in some sense, the universal function evaluated at L. If you have trouble making sense of that, let me write it in terms of a coordinate. It's really the universal function written as a power series in X and evaluated at the Euler class of L. I just did something, by the way, highly abusive, which I used gamma univ in two different inconsistent types. This is a function on the formal group. This is a power series in some variable. So whatever this gamma univ is, it really somehow depends on X. It's the power series expansion of the function at X.
What's the subscript on the O?
The subscript on, where's the O? O here? OG. So G is some formal group. One that's base change from F0. Okay, so far so good. So this is just
These BKs are group-like or primitive?
BKs.
These classes, BKs.
Sorry? Oh, the B sub Ks?
Yeah.
They're elements. There's a coproduct. I didn't write down the coproduct, and I could write down the coproduct. Here it is. Delta star. Everybody knows this, right? What's the coproduct? Somebody tell it to me because I can't figure it out. This is the one, right? It's the sum of BI tensor BJ? Yeah. That's it. Why is it this? Oh, because it's all these things really live on BU1, and BU1 has a diagonal map because it's a space. So I'm really just computing the coproduct on BU1. The coproduct on the homology of BU1 is dual to the cut product on the cohomology of BU1. And I told you what BU1 cohomology of BU1 looks like. It's a power series ring, so I know how to multiply things there. So I think, yeah. All right. So, oh yeah, so I was going to make, suppose I have a bundle that's really a sum of line bundles. Well, then I get to write this universal class as a product of the values, the Euler classes of the individual terms. And more generally, I can apply the splitting principle to compute this universal class for any vector bundle by pulling back to a place where I can split up the bundle as a sum of line bundles. Everybody's seen that method. So this is sort of the universal place where you can do this kind of operation. So for instance, if I took E to be ordinary integral homology, but let's say made periodic, so if it's in this scheme, then I could choose particular functions and extract multiplicative characteristic classes. If I take just the function x, the standard coordinate, I get the Euler class. And if I take the function 1 plus x, I get the total Chern class. So this formalism includes those ways of building characteristic classes that are familiar. All right. So this is just getting sort of used to thinking about this object. All right. So now I want to compute a power operation. All right. So I'm going to use the space BV. So as I pointed out here, it's an E-infinity space. Leave that up. All right. So it's an E-infinity space. So let's assume now that E is a commutative S algebra. Now we also have the suspension spectrum of BV. BV is an E-infinity space. Therefore, that is an E-infinity ring spectrum. I'm going to take the notion of E-infinity ring spectrum and commutative S algebra to be synonymous. Because if you have an E-infinity ring, then if you're in a particular world of spectra where you have commutative S algebras, you can find a model that really is strictly commutative, which is an E-infinity. So this is an E-infinity ring, aka a commutative S algebra. And therefore, so is the Smash product. S algebra. So it's going to have power operations. So I can look at, let's think about computing the cohomology operation induced by a power operation. So I'll have a space X. And I have a power operation. And this is going to land in F0 of X times B of the symmetric group. And so what I'd like to do is I'd like to compute PM of some elements. I don't know how to compute PM of a general element. That's much too hard. However, there's a particular class of elements I can definitely compute PM for, namely the ones that are actually these characteristic classes, these universal characteristic classes or tautological characteristic classes. So I'm going to compute this on those elements. And so the theorem, it's a proposition, it doesn't deserve to be a theorem, is the following. The power operation applied to this class, so I'm starting with a vector bundle, is equal to another characteristic class. It's V, all right, a box, and then rho M. Rho M is the permutation representation of the symmetric group. Well, if I have a representation of a group, that automatically gives me a bundle over its classifying space by the Borel construction. So this is also the bundle, the associated bundle, Cm cross over E sigma M, cross over sigma M, E sigma M, back to B sigma M. And then this tensor is the external tensor product of a bundle over X with a bundle over the B sigma M. All right. Well, so I guess I can prove this, but the observation is that these classes are special because they're actually defined using maps of spaces. So let's do that. So if I start with a map of X into BV representing my bundle, I can apply the space level power operation, which uses the fact that BV is an E-infinity space. So I'm using that E-infinity structure. So I start with X going to BV, representing some vector bundle, and then I take the m-fold power, this is a product, and then I symmetrize this. On the one hand, BV is an E-infinity space, so I have a refinement of the m-fold Whitney sum to a function like this. I'll call it Whitney sum again. But it comes to the fact that it's an E-infinity space. And then I have the diagonal inclusion, X into B sigma M. So if you forget the symmetric group part, just think about the restriction to X times a base point. This is clearly just defining the V-fold direct sum, the M-fold direct sum of V over X. But there is a group action. And that's a symmetric group action. Yep. No? Okay. So this exactly represents the bundle V direct sum M. That's the pullback of the product bundle to the diagonal. Well, this thing. And the way it depends on B sigma M is just through this group action, so I can rewrite it as this tensor product. All right. And then, in fact, this is only a space level construction, but it's really computing the construction I want on the ring spectrum, because there's a commutative diagram. So I have this. I'll write H to the M, H sigma M. And this goes to the suspension spectrum of BV sigma M. But this goes to F smash M H sigma M. F is also a commutative S-algebra. It has this multiplication, and that extends the one that's already defined for BV, because the map from the suspension spectrum of BV to F is itself a map of commutative S-algebras. So this map down here is the suspension spectrum of the map I just told you about. And now I'm just pushing it forward into F. Well, that's the definition of the of this tautological characteristic class of that guy. All right. So
I guess another way to say this is that for this particular relation, it's not relevant that E is even commutative, and it actually happens already when E is the sphere spectrum.
Yeah, that's one way to say it. Already have. I mean, I didn't use anything but E. In fact, so this particular stuff doesn't even. I mean, the definition of bracket doesn't use anything at all, so I don't even need to be even periodic, right? If I want to understand what I got, I probably want E to have something that makes it computable. But so far, this is just purely formal. Now, if you do want to compute this, it turns out that it's handy to consider the following restrictions. So I have here the permutation representation on the symmetric group. But let's consider a subgroup of the symmetric group. And I want this to be a transitive abelian subgroup of the symmetric group. So it's abelian. Transitive is in reference to the tautological action of A on the M-element set. It acts transitively. So A acting on the M-element set is a transitive action. So I obtain here a characteristic class that lives in the cohomology of X times B sigma M, but I can restrict this now to the cohomology of X times the abelian group. So for instance, I have the representation of the symmetric group, and I can restrict it to this abelian subgroup. Well, the permutation representation becomes a regular representation. This actually becomes the direct sum of one-dimensional representations. So it's right here. A hat is the dual group. And I'll identify the homomorphism to C cross with the associated one-dimensional representation. So if I...
Are you saying A is cyclical? Because there are other transports between subgroups.
I never said it was cyclic. Did I say it was cyclic?
No.
Where is it cyclic?
Okay, so but this holds even if it isn't.
Yeah, it holds for anyone. In the end, I'm only going to care about one example, which is when M is P, and then there's only one such subgroup, namely a cyclic group. So if you like to think about cyclic groups, that's a good thing to do. But oh yeah, they all have order M. That's a fact about transitive abelian subgroups. Sorry. So this is it acts faithfully and transitively on an M element set. So it has order M. All right. So what this means is that if I take this rho M thing, but restrict to x times BA, well, this becomes this, which I can rewrite as a product because my angle brackets behaves well on sums. So this is this operation. In particular, I could apply this to the universal line bundle. Ugh. Right. Hmm? Right, so if I take the universal line bundle, so we get product of this. And it's convenient maybe to write this in terms of, well, we know what brackets L is. It's the universal function. I should put univ here. What's brackets this? Well, it's a tensor product. So it's described in terms of the formal group. So if I write this out in terms of a coordinate, I get a product involving the universal function. And I'm going to think of it as a power series in X, because I'm going to use the Euler class of the tensor product. And I can rewrite this as gamma star univ of the formal sum of x of L and x of lambda. In fact, I think I said that this was just x. That's my formula for a formula for that. Okay. So I've computed the power operation in F on really on one class, which is the universal function. Okay. I did this here, by the way, where this was the base space was BU1. So this was a power operation on F0 of BU1. And this therefore lives in F0 of BU1. Oh, and I restrict it to BA. So that. All right. Great. Goodness, I'm going very slowly. All right. I knew I would. That's not a surprise today. So what I'll do next is I'm going to let E now is going to be Morava E theory. So I want to relate this to the machine I've already talked about for power operations for Morava E theory. So far, this was an arbitrary ring. The particular calculation doesn't really use anything. But now I want to use this. Now I'm going to take F. Well, there's a little problem because that machinery required that my ring spectrum be not merely a commutative E algebra. it also had to be KH local, where H was the height of the finite group, of the formal group. So I have here a formal group of height H, and I'm going to define F hat is the KH localization of F, which is the KH localization of E smash suspension spectrum of dV. And so one thing we need to know is what the homotopy groups are, and luckily this is pretty good. These are exactly, this is exactly the original ring F0, but now I complete at the maximal ideal inside the coefficient ring of E. So that's a calculation with it in this case, or if you like. KH localization could in principle be much more difficult to compute, but in this case it does something very reasonable. And this ring still represents functions on the formal group. Only now it has a topology, and so when I talk about homomorphisms between rings, I mean some kind of continuous homomorphism. In this case, it would be the topology just given by the M-adic topology. All right. So I'm coming up to the break, so let me just say something before then. So I want to describe the descent for isogeny structure on F0 hat. So remember, this ring represents the functor. So it's an algebra over E0. So in particular, it represents a deformation of my original formal group G0. So this is a functor that takes R to the data of I don't even understand what I wrote here. What do I want to say? How do I want to say? What I want to say what this ring represents, a homomorphism from F0 to R. Let's write it like this. I don't know what I wrote. I wrote on the notes. It's stupid. Let me see a better way. So homomorphism from F0 hat to R, some kind of continuous homomorphism, coincides to the data of a deformation of G0 to R in the sense of the previous talks. And the additional information is a function, I'll just call it gamma, on the function ring of this deformed group G. Very often, I'll fix an E0 algebra structure. Remember, this thing contains E0. And if I fix the E0 algebra structure, that's fixing the deformation. So I'll just think of this as representing the function. All right. Now, because I have power operations in Moravi E theory, that means, by the theory I described earlier, that this functor that it represents carries the structure of descent for p power isogenies. So let me say what this means. Let me rewrite what I just said, since it's more sensible to say it this way. If I take a continuous homomorphism of E0 algebras from F0 hat to R, that set is canonically the group, the ring of functions on the group G. So remember, where the E algebra structure is the one that classifies the particular deformation. So that's what the G is. It's the E, given by the E algebra structure. So descent for isogenies says that for every isogeny, F from G to G prime, between deformations, there's an associated way to push forward an element in here for G to a corresponding element for G prime. So there's a corresponding push forward. It's just my name for the map. F lower shriek. This will go from OG to OG prime. So this goes in the opposite direction that functions usually go. I'm not pulling back, I'm pushing forward. Okay, so I want to determine what this function is. There are some obvious properties that it has to satisfy just from the formal setup. So one property, remember that, well, OG is a ring, so there's some operations on it, like addition and multiplication. But only one of those operations really comes from something fundamental. I pointed out earlier, the multiplication in OG was represented by the diagonal map on BV. So that's a map of spaces. That means that there's naturality with respect to that map. That means that F lower shriek is multiplicative. So before doing a computation, I know that F lower shriek takes a product of functions to the product of the values. It's multiplicative. That's just because that's what the coproduct on BV is. It's a purely natural thing. What else? Oh, there's one other thing that this descent for isogenies came with. It came with the Frobenius congruence. The Frobenius congruence says that if I have an isogeny which actually is the pth power Frobenius, so this is a map from G, so G is defined over a ring R which is of characteristic P, and then I have a map to the Frobenius twist of G. This is an isogeny. This is the relative pth power map. Then the Frobenius congruence says that F lower shriek of a gamma, if you trace through what it means, it says that F lower shriek of gamma is actually the pth power of gamma. I think if you think this through a little bit, you may have to adjust what I write here, because gamma is a function on G, and the target is a function on the Frobenius twist. So I think I probably have to do some funny twists with the coefficients in the way you often do when you talk about these things. But I don't seem to have the right formulation here. So I'll leave that as an exercise. OK, so those are some properties. But we can actually say what the thing is. So I'll say what it is, and then we'll have a break, and then I'll prove it. What is it? Well, an isogeny induces a map on functions. It's in fact determined by the associated map on functions. It goes the other way. It's F upper star. Because it's an isogeny, let's say of degree p to the r, this map presents O of G as a finite and free OG prime module of rank p to the r. So this presents as a finite free OG prime module of rank p to the r. In fact, particularly this is an inclusion. That also happens. Here's the theorem that tells you what F lower shriek is. F lower shriek of a function. So F lower shriek is going to be a function that goes the other way. I'll put it in dashes because it's not a ring homomorphism. So I take a function on G. This is going to be NF of gamma. N stands for some kind of norm. This is just the determinant. So this is the Galois norm along F upper star. In other words, if you take your function gamma, you think of it as multiplication from OG to OG, multiplication by gamma, and you take the determinant, if you think of it as a map of OG prime modules. So the determinant of that matrix is an OG prime. And that's the definition of NF of gamma. So that's what the theorem is about the power operation. This describes power operations on the E homology of BV. The push forward is this multiplicative transfer you can define by this norm. So I'll try to connect the dots in the next part. So let's break. I'm not sure who this is due to. I mean, all of this is implicitly in Matt's original paper. I'll say why it's all right. All right. So let me discuss the proof. So the claim was that, this descent for isogenies map, this push forward, was given by the determinant. Okay. So of course, I only have to compute the universal example. That's how you do these things. So I have the universal example of an isogeny going from some pullback of the universal formal deformation to another one. This lives over a ring, which I called AR. Remember that this was some quotient of a symmetric group, cohomology of a symmetric group by an ideal. So the universal example of a function is represented by, well, what I want to compute, I'll just write it like this. Let's just say that the associated to this is the universal operation. So the ring spectrum is or f hat, excuse me, and there's this operation psi r, which goes to f hat 0 tensor over the coefficient ring with this ring AR along S. So this is the base scheme where S star G universal is defined. This map therefore represents some kind of function in on S star of G univ. I'm sorry. Grr. Oh, I'm going to have trouble saying this. I want to compute this map. Let's just say that. Actually, let's think about this differently. This extends up to a map from the tensor product of f0 hat with AR, but along T. This function is the one associated to this. I see. I think I want to say this. So there's the universal function lives on the universal formal group, tensored up to f hat, and therefore I can pull it back to the source of this isogeny, but also pull back to this ring that carries the universal function. And the claim is that this is a tautology that I'm somehow not being able to unravel. Psi r claim, let's just leave this as a claim. Psi r represents f lower shriek of this universal function. And this is an element in O T star G univ, base changed up to f hat, which carries the universal function. It's always a little bit surprising because you do something and it involves something that has an S in it, and it turns out to have to do something with T, the target.
What is that I up there?
What I? The ideal. This is the transfer ideal. It's the ideal generated by transfers from subgroups, proper subgroups of the form sigma I times sigma p to the r minus I. So this is a transfer ideal. It's always surprising that somehow I was supposed to write something involving T, but it lands in the thing with S. But the thing to remember is that there's the usual inclusion of E0 into f hat, and the composite actually classifies the target. So when I say I have this map, it's classifying some information about the target of the universal isogeny. And the information it classifies in this case is the direct image of this universal function. That's just a translation of the formalism I described last time to this example. I think, since I can't seem to actually recover a better statement. But let's just take that. We have the following diagram. So let me write down the map I have, psi r. F hat tensor over E0 AR. And this represents F lower shriek of the universal function. We just call it the universal function. But this is the F0 hat cohomology of a point. I can also consider the F0 hat cohomology of BU1. And then I also have the F0 hat cohomology of BU1 tensored up. The vertical maps just come from the topological map, induced by pulling back on the projection to the base point, so it's inclusion of scalars. This is a different psi r. It's the one for power operations on the cohomology BU1 with this cohomology theory. This will take, now this object is the ring of functions. It contains an element which is the universal function. That's where the universal is. The universal function is an element of here. And I can apply the power operation. That gives me an element which I'll call psi r of gamma univ. It's in here. Let's call it delta. The claim, I want to figure out what this target is. It's some function on a formal group. If you trace it through, this is a ring of functions on S star of G universal, although also pulled back from E0 up to this ring F0. And so you might wonder what this element is. So psi 1 gamma univ, that's actually what you get if you take the push forward of gamma univ defined by the power operation and then pull it back along F upper star, which is the usual map restriction of functions. And that's a function on O of S star G univ, base changed up to F0. Okay. That's the claim. Psi 1? Is there a psi? Oh, psi r. Sorry. We could actually just restrict to psi 1. That's the only one we need to compute. All right. So given the claim, so the claim will then allow us to figure out what F lower shriek of gamma universal is. Because remember, it's still up here, F upper star, the restriction on functions is injective. So this thing's only computing the restriction of F lower shriek, of the thing I want to compute. But it's an injection, so I'll know its image in the ring of functions on the source, and that will give our calculation. So let me prove this claim, and then I'll do the calculation of what it is. All right. And we'll see how well this goes. Let me actually get some more. All right, so I need one more little bit of notation, which is the points, the R points of a formal group, G over E. My formal group is going to be a deformation. So GR is going to be defined to be the set of continuous E0 algebra homomorphisms from, so this is a deformation, so it's classified by a map. A deformation. And so this will be the E algebra maps from the cohomology of BU1 to R. A point is a ring homomorphism from the ring of functions to some ring. That's an R point. So I'll take an element here, a P, that's a point. If I have an actual function that is an element in E0 of BU1, it makes sense to take my function, gamma, and evaluate it at the point P. What is that? Well, that's what happens if I take my point, which is really a homomorphism, and I compute the image of gamma along that homomorphism. In other words, gamma of p is defined to be p of gamma. Yeah, that's the usual nonsense. Right, okay. More generally, if I take a map E0 BU1 tensor over E0, let's say a hat with F0, so that's really F upper 0 of BU1, and I take this map. So what does a map like this classify? This is a ring homomorphism. So it classifies a deformation G, that's the E0. It classifies a function on the function ring of that deformation to R, and it also gives me a point. So this classifies a deformation, a function on the function ring in the function ring of the deformation, and then an R-valued point of G. This domain has a particular element, namely the universal function, gamma univ. Where does this homomorphism send gamma univ? It's got to be an element of R. What it's going to do, it's going to send gamma univ to gamma of p. So it knows about a point in a function, and it's just the thing that evaluates the function. Let me just put this here. This sends gamma univ to gamma of p. So we'll save that idea for later. All right. Now, what I want to do is I want to compute psi r. I erased my theorem. So I want to have here now, let's take psi r. So I'm going to break up F0 hat of BU1 into a tensor product. There. Here's psi r. Here's F0 hat of BU0 again, but now I'm going to tensor it up to AR. And now suppose I give myself a ring homomorphism. What does this phi classify? Starting from right to left, it classifies an isogeny between deformations. So F from G to G prime, defined over R. A function on the domain, on G. So gamma in O of G, and a point in O of G valued in R. So P in G of R. Yay. There's a composite. What does this classify? It's going to classify, well, there's a formal group here. The formal group involved, the deformation is G prime. I said this earlier, the inclusion of E0 into F0 hat followed by the power operation always classifies the target formal group. So this classifies G prime, the deformation, and then there's going to be a function, which I'll just call gamma prime, on O of G prime, and then there's going to be a point. And I can say what the point is easily enough. This is a point in G. This has to be a point in G prime. There's an isogeny F. If you check, the point is F of P in G prime valued at R. So I didn't tell you what gamma prime is, but that's also sort of has a name given by the formalism. I haven't really computed it. Gamma prime is exactly the thing that we want to compute. It's F lower shriek of gamma, gamma univ. Or sorry, just of gamma, because I had a gamma over here. So this is just saying that, F lower shriek by definition is whatever this map classifies on, or the original map psi r on F0 classifies. I'm just reading that off. Okay. So the idea is that now I have this little diagram. I want to take the universal function, which actually lives in here, and I want to follow it through. Remember, I cared about its image. I call this delta. This is psi r of gamma univ. Question mark. I don't know what it is yet. But I can follow through its image down here. What's the image of this thing down here? Well, I think about this map, and I think about this recipe for computing it. This was the recipe for computing the long map on the universal function. The rule is I evaluate the function at a point. So this thing sends the universal function to the function gamma prime that got classified, evaluated at the point. The point is f of p, where p is the point that appeared here. Well, that, therefore, because diagrams commute, these do, delta goes to that. Okay? What do I conclude from that? Well, delta is some kind of function on S upper star of g, pull back to f0. It's a function. I can tell you how to evaluate it at p. The rule is, let me do this on the other board. I just computed this. It's a little bit confusing because I want to say I'm going to evaluate delta at something, but delta itself depends on gamma, because delta is not really a function on t star of g univ. It's a function on t star of g univ base changed up to f0, which is the place that owns the universal function. So, and if I have a map from all that stuff that in particular classifies a gamma, that has to show up. So what I've shown, because of that arrow on the right, if I take delta, which secretly depends on gamma, and evaluate it at p, that's exactly gamma prime of fp. So now let me get rid of the point. What this says, the point p, this says that this function delta is the pullback along f of gamma. Delta is the base change along f of gamma prime, excuse me, it's a gamma prime, and gamma prime was just a shorthand for f lower shriek. There. So, of course, this was a particular gamma given because I had some homomorphism, but really I'm computing this on the universal example. So the universal example will give me that. So I prove this claim, or browbeat you into believing that I can prove it. Right. I was wondering whether I should even try to give this argument, because it's one of these arguments that's both tautological and sort of takes like 4 or 5 hours to figure out. And I can't really do anything about that. It's just, it's that sort of thing. Where did I use Moravia E theory? I don't know. What line did I use Moravia E theory at? So I used it in several ways because I need to know these things represent the appropriate gadgets. You know, in a sense, I'm not using very much about Moravia E theory. You should think of this as something that's really generic. And I only know how to prove the theorem for Moravia E theory because I have names for what all these rings represent. But in some sense, it doesn't feel like this is something that actually depends on Moravia E theory. It's a more generic fact. So I don't think I can point to you the place where I use it. It's Moravia E theory. You might imagine you have some other theory you could apply this to, but.
But you do use it when you pick out G prime here, psi r. I mean, you're using the limitate moduli problem to get.
I mean, to describe what all these rings represent, I use the fact that I have Moravia E theory, not just E0, but AR and all these things. But yeah. Is there another question? Okay. So I think there's actually a point. It's hard to, you can't really point to where you use Moravia E theory. It's something a little bit more generic is going on here. If I had an equivariant theory and I could name, I was doing equivariant sigma r, cohomology for some E, and I could name all the rings, I would expect to be able to do the same argument, as long as I could figure out what an isogeny is.
What did you by name all the rings?
Well, I said that AR was the universal thing that carried a different, an isogeny of a certain type. I mean, I need to know those relationships, or at least to understand that it has a canonical isogeny that lives over it. Let's not try to work this out now, because I don't think we'll prove the theorem that way. So where was I? So I computed that. So now I just have to understand what this is. But now the first, so what I was doing earlier, which is also kind of a generic argument, was, so remember, this had another name. It was this tautological characteristic class of the universal line. So let me leave that up. I'm working a different board. Ugh. All right. All right, I don't want to take forever with this, but all I have to do now is connect up with the calculation I already did. So for general theory, what did I do? I had a gamma univ, which was the brackets of L univ. Oh yeah, so that lived in F0 of BU1. I'll put a hat on it because now I'm in a KH local world, but effectively everything is the same. And I computed things like the power operation. Let's have this be P to the R. This was PM. And I said that PM sent this to something like this. And now I'm going to pass to the quotient by the transfer ideal so I can get ring homomorphisms. And this goes to an element which I won't name because it's basically the same thing, mod I. And this, put the hats on everybody, is the function psi r. So I've already computed the image of the universal thing. It's this. But now I want to now figure out, I want to prove the theorem. The goal is to prove that this F lower Schriek is actually this determinant. The way I'm going to do that is restrict to some appropriately chosen abelian group, BA, a transitive abelian subgroup of, now I will erase the other board, the other half, of BA. Do that again. So we'll choose some convenient transitive subgroup. And in fact, because a power operation, as I explained last time, was for Moravia E theory at least, is entirely determined by what happens on sigma p. I can really just reduce to that case. So I could actually use the cyclic group of order p here. And there's a corresponding transfer ideal in here. I'll use the same name. They're different ideals. Okay. And I computed the image of this, sorry, wrong, in here. This was this product over the characters on this finite abelian group A. Now I want to identify, I want to show that, well, I wanted to show that F lower Schriek of any function is this determinant of that function. Although since I'm pulling back along F upper star, that's what I'm going to prove. Now, let me not belabor this. Let's just think about an easier situation where I actually have physical groups. So suppose I have an exact sequence of actual groups and sets, abelian groups, exact sequence. So in this setting, I could think about functions on these groups valued in some ring, commutative ring. Let's not worry about what ring. So,
can I ask one thing?
yes?
You usually have to be careful if you mod out transfers, and restriction to subgroups isn't really always well defined anymore. Why does this work here?
Restriction to subgroups, because this ideal goes into this ideal.
By definition, because you define this as an intersection, or?
It's the push-pull formula for transfers shows this. The transfers, here I'm taking the transfers with respect to all proper subgroups of A. Here I'm taking the transfers with respect to all these subgroups sigma I times sigma j. But you can factor the diagram, that diagram of spaces, in such a way so that you can see that the transfers has to factor through.
So that's something special for this particular situation?
So it turns out, basically there's a game you play. The kinds of things you always put here are subgroups of a symmetric group, or things that have and are equipped with an action on an M-element set. Associated to any such group is a transfer ideal. They're all defined the same way. They're generated by all the bundles, all the sort of the covering spaces you get by pulling back the ones that define the transfers on the symmetric group itself. So whenever I write down transfer ideal for any group with an action on the M-element set, there's an associated transfer ideal, and they're all defined in a uniform way. So this map is defined. Okay.
You have a subgroup of this transitive subgroup that it would, if you interpret that it would not be transitive anymore, so it's split up as a product.
Yes, that's the point. Yeah. The proper subgroups of A don't act transitively on the M-element set, so they're inside whatever I had here. But an exact sequence of groups, what was I saying? Well, there's a norm here. This is going to be a finite group. So maybe this is F. There's a norm. You can define it explicitly. You choose a set section, and a set theoretic section, and then you can use the characteristic function of the image of that, and it translates by A to describe a basis on the ring of functions. And then you can write down the matrix, and it's a determinant. And you discover you can calculate, in this case, that if you pull back the determinant operation applied to some function, this always has the following formula. It's what you get if you take the product over all the elements of this subgroup, A hat, of the translations. Let's write it like this: gamma of G plus, let's call this I, so it has a name, plus all the i's of lambdas. That's the formula for the determinant in the case where you actually have physical discrete groups. Now, in our case, we don't have physical discrete groups. We have some kind of formal groups. The observation is if you take this gadget, if you invert P, the formal group becomes a discrete group. So I'm going to, let me not, because I'm running out of time and fuzzy right now, fuzzy-headed, let me not try to spell that out. If I invert P, I can turn my formal group is also a P divisible group. And if I invert P, it becomes an étale P divisible group. And if I enjoin some roots of some equations, then it's actually a discrete group. And if I compute the formula, the norm formula, or if I think about whatever the norm formula is for my formal group, and I pass to this place where I actually have a discrete group, that's the formula. On the other hand, I wrote down a formula for the actual power operation in terms of the line bundles. And I got this formula. This formula is the same as this formula. That's more clear if you think of this in terms of a coordinate. Or say, if I think of this in terms of a function. If I wrote this actually in terms of functions. So if I call this the universal function, then this was actually gamma of the universal function applied to the formal sum of x plus x lambda. That's what it was. It's that formula. So you have to do a comparison. And this comparison happens in the place where you can replace the formal group by a P divisible group that's actually étale. There is none. This isn't the additive group.
You're saying if I take a formal group, then after phase with flat phase change, it becomes
Sometimes. So I have to be a little bit careful, though. If I take a formal group and base change, I just get another formal group. But I take my formal group, which is this deformation, and I realize that the ring of functions is actually an inverse limit of quotient rings, which are the functions on the P to the R torsion. The functions on my formal group are the inverse limit of certain quotients, which are, if you like, divided by the P to the R series. Now, in the case, That's not always true. That's only true for a formal group on, say, on a cohomology theory that's P local. You have this kind of formula. Maybe I should say P complete. It has this formula. But in our case, it's even better. For my formal group that's a deformation of a height n formal group, this is a finite group scheme. So this ring, if you write it out, you could actually write this as E0 adjoin x divided by a polynomial, which depends on r of some degree. So degree p to the r times h. So that's a finite group scheme. It's a monic polynomial. It's actually a finite flat group scheme. So the system of these things forms a p-divisible group. And that's the object I can base change to other places. Like I can invert p, and all of a sudden they become a-tall group schemes. So physically, the way you see it is that you can solve this equation over some extension ring. And those are the points. I don't want to say too much more because I won't be able to make a story that sort of, we can talk about this after. Or more, you could consult Nat and let him describe it to you because he understands this how much better than I do. So there, we've got the recitation all worked out for you. All right, so I only have a little bit of time left. So this was the end of the proof. So this identified the power operation for this space BV in terms of something involving the formal group. And this turns out to be something you want to know. I guess in principle, you could turn this into something that you can calculate, because you can calculate these kinds of norms if you have enough control over what the formal group looks like. But there are other things you can do. So let me relate this back to where I started, which was the theorem of Ando, Hopkins, and Strickland. So I think I said this already. I just did a calculation for BV, the classifying space of vector bundles. But BV has friends. Here's some of its friends. Well, BV maps into Z cross BU, the classifying space for virtual vector bundles. That has a Posnikov tower. Over it we have BU, we have BSU, we even have BU6. And then there are other friends here, which are the Thom spectra associated to these things. This one you don't usually think about, the wedge of the MUMs. Then you have something called periodic MU. Then you have actual MU. And then you have these variants. These are the friends of BV. So I did the calculation for BV. I observed that it represents functions. So let me right now write down the functors that the homology of these things represents. This represents functions on the formal group, whichever formal group of E. This represents invertible functions. That's Z cross BU. Let me go up one more stage right now. This represents invertible functions. Oops. Goes like this. One way to say it is it's invertible functions divided by scalars. So there's the ring of scalars inside here. I'll make those identifications. So that's a quotient map. It's sometimes convenient to think about this as the function, invertible functions whose leading term is just 1. But if you look at this picture naturally, the natural map here is this one. It's the quotient map. Okay. And then there's more stuff, which I'll call theta 2 of G, OG, and theta 3, G, OG. And there's a similar story here. This thing was the ring of functions. This thing is an ideal in the ring of functions. That's what it represents, the wedge of MUs. This is the ideal. That's the ring of. It's the ideal of functions that vanish at the identity element of your formal group. Associated to this is what I'll call the trivializations of I. The ideal is a rank 1 module, free module. A trivialization is a basis element. And over here, I'll have what they're sometimes called rigid trivializations. So I guess if I think of it as a quotient, it's trivializations up to scalar from the base. Or sometimes, if you like to think of this as corresponding to functions with leading coefficient 1, then you'll probably want to think about this as trivializations that have some specified behavior at 0. Okay, let me not write all that out because it's not really relevant. All of these even have universal examples, right? There was not only did the E homology BV represent functions, there was a universal function. And we can write all these universal things out. I'll write out the ones for the BUs at least. So for BV, this was the universal line bundle was the universal object. For Z cross BU, 1 minus the universal line bundle. That's the thing that's the virtual bundle that is represented there. No, that's wrong. That's actually just the universal bundle again. Wrong. BU, that's 1 minus for this gadget, for BU, this is 0 cross BU. This guy is 1 minus the universal line bundle. That's the universal gadget for.
Why did you choose that sign? Why would it be the universal line bundle minus 1?
So I'm doing, you did 1 minus L universal because that's the way they write it in their paper. Possibly that's the wrong choice and they should have written it the other way. I would not disagree with you. The AHS paper. For the purpose of this discussion, it won't matter because I'm never going to say anything specific enough about it. So if you want that to be L minus 1, that's fine.
You want BU1 again, or you wrote
I wrote BU1, sorry. And let's see, what's the universal object here? I didn't tell you what theta 2 is, so I won't tell you what the universal object is. Let me just stop here. So in each case, there's an associated formula for power operations. All of these objects are all E-infinity spaces. Their suspension spectra are rings, commutative S algebras. These are commutative S algebras as well. And in every case, there's an associated formula for pushing forward something along an isogeny corresponding to power operations. It's always a norm construction. I'm not going to write them all out. Consult the paper. But here, it's really obvious. You have an invertible function. The formula I gave down clearly sends invertible functions to invertible functions. That's the push forward. It clearly passes to this quotient, invertible functions mod scalars. It's a little bit harder to say what happens when you have this ideal. But you can also write down a norm operation on each of those things. And that's the recipe for how power operations act, or how E-theory power operations act on all these things. All right. So for instance, Ando's thesis was in some sense about structured ring maps from mu into E, wherever E theory. So I define this notion of an H infinity ring. Maybe let me say what an H infinity ring is. So an H infinity ring is an algebra for the monad P on the homotopy category of spectra. P is the homotopy category, it's the derived functor, if you like, of the functor that describes the free commutative S algebra. So we have a functor that takes a spectrum and gives you the free commutative S algebra. It looks like that up to homotopy. It's the direct sum of the nth powers of x divided with the homotopy orbits by sigma n. And that induces a functor in the homotopy category, and there it's a monad. And algebras are H infinity rings. And there's a notion of H.
What's the subscript under that big wedge?
N greater than or equal to 0, maybe? All right. Any commutative S algebra gives you an H infinity ring structure. You're just sort of forgetting that you have this very rigid stuff, but you're remembering you get this algebra over this monad in the homotopy category. And so, let's see how I want to say this. So he proved, Matt Anzo's thesis, if you go back and read it, really solves the following problem. It classifies H-infinity structures on Moravia E theory, H-infinity orientations. So the class of H-infinity maps from periodic mu to E, and this is a Moravia E theory, corresponds, so this is pi 0, it's just a set. It corresponds to the set of coordinates for the formal group of E that are consistent with norms, so which are compatible with the norm construction that I just described. Let me spell it out a little bit. So if I give myself a coordinate on the universal formal group, this is the ring of functions on the universal deformation, rather, of G, then I automatically get a coordinate on every deformation because it's the universal one. So an x in G univ gives me a coordinate, an OG univ, a coordinate, gives me an x Gi alpha in O of G for every deformation. Gi alpha. And being consistent with the norm says the following: if I have an isogeny of deformations, then if I take a coordinate, this coordinate on G produced by this choice of universal coordinate, and if I apply this norm that I described, so that's going to give me something on G prime, well, that should be the same as the image of the universal coordinate in O of G prime. So a coordinate on the universal group gives you a choice of coordinate for every orientation, and they all have to be consistent under this push forward given by this norm. That's the condition, and that's exactly what an H-infinity orientation of E is for MUP. He also showed that, at least for certain Moravia E theories, I'm not sure exactly if it works for all Moravia E theories. I wasn't able to determine that before it was time to give the talk. He shows that for certain of them, there exists an H-infinity orientation. It's probably for all of them, but I'm not sure how well that proof works to prove it for all of them. Now, what you should think of is that an H-infinity map is sort of the shadow of what you have if you have a commutative S-algebra map. So if I have a commutative S-algebra map from MUP to E, that is a commutative S-algebra orientation of E theory, then I automatically get one of these structures. And you might ask, is the converse true? And somebody had an answer.
Is that false?
I don't know if it's... do we know that it's false?
No, I guess not.
I don't know that it's false. There's every reason to expect that there are more obstructions, but I don't know an example. Certainly not known to be true. That's different from being false, I think. So Barry Walker proved that it's true when E is p-adic K theory. That's kind of a sign that sort of there are no further obstructions, but we actually expect for even that height 2, there's at least a further obstruction you have to contemplate to decide whether this is true. And as the height increases, it presumably gets more complicated. This is sort of, as far as I know, it's an open problem. I always sort of imagined in my head for a long time, oh, we must know that because we have this coordinate, but it only gives you an H-infinity structure. All right. Oh yeah, so I'm almost out of time, but let me relate now back to the story of the Inno-Hopkins and Strickland we're actually doing. So this is MUP, and there's a similar story for MU. But I put 2 more things up there. I have MU SU and MU bracket 6. And I have these things called theta for the B's. And I didn't write down something for the M's. I could also have written thetas. These will be theta 2 of G, but with I, and theta 3 of G with I. What are those? Let me leave that up. Let me just do it for the B's. So theta k of G is the following thing. Theta k is a collection, sorry, is a certain kind of function on, I'm going to have to end very soon. So E0 BU brackets 2k for k up to 3 and no higher represents theta k G of G. I have to say what this is. This is a collection of functions on a k-fold product of copies of G. That's right. It's a function on the k-fold product copies of G, such that I get, let me put 1 here. It doesn't work for 0. If I evaluate at 0, I get 1. It's symmetric in the inputs, the k inputs, and I have the following identity, which I'll write like this. F of x1 plus x2 comma x3, and then there are higher terms here, times f of x1 x2, and then the same higher terms equals f of x1 x2 plus x3 higher terms times f of x1. This is nonsense. I think I'm supposed to put x2 x3 here. All right, it's a set of functions. There's a similar description for theta k of gi, where instead of using functions, I use sections of a bundle. Okay. And so they prove a theorem that says that. They prove 2 theorems. The first theorem is not about H infinity or anything. It's just about ring spectrum maps. After all, I even know for MU, I know how to classify a plain old ring spectrum map from MU into any even periodic ring. That's a coordinate. Similarly, so I said that algebraically this represents this function, but in fact, there's a topological fact. For E even periodic, E is even periodic, the space of ring spectrum maps, that's a set, not a space. This is just something that you can define in the homotopy category from, let's do this for MU. It's also true for BU. K into E. This again for K from 1, 2, and 3 is in bijective correspondence with these sets. In this case, it would be theta k g I. This is the formal group of E. Okay. So it gives a classification of these things. So Hopkins-Strickland 1. It's one paper. And they have another paper where they extend this to the H infinity setting. And they say that H infinity maps well, it's the collection of elements in this gadget which are consistent with norms. Let me not write all that out. And if you've looked at the paper, you see why I don't want to write it out. Kind of hard to say. Although in some sense it's easy because it's just consistent. Okay. Why do I only go up to 3? Because these spaces, BU, BSU, and BU bracket 6 are even spaces. Their homology, in particular, are free abelian groups concentrating even dimensions, and that breaks once you go higher. So you can't push this particular kind of style of thing further because you lose control. The ring, the E homology or whatever, is not likely to be a very nice object as you go up. Yep. Yes.
So in the E theory case, you have this trick where because you have a coordinate on the universe conductor, you get a coordinate on every
Yes?
It's not clear to me how to, given a coordinate on one elliptic curve and an isogeny.
I didn't have an elliptic curve yet.
Huh?
There's no elliptic curve yet.
Oh, crap.
E is a cohomology theory. Here it's a cohomology theory. Here I should have said it was a Moravi-E theory in the second line.
Oh, okay.
It's a cohomology theory, not an elliptic curve, which I've usually tried to call C for that reason, although not always. Okay. Blah, blah, blah. Okay, why is this a good thing? It's because of the following fact. Now I can bring in an elliptic curve. An element of theta 3 coefficients in I is called a cubical structure. I believe this definition of a cubical structure is due to Larry. Is that right? And it's a classical fact encoded by this structure, which you can code once you have this structure, that every elliptic curve has a unique cubical structure. So of course, I've defined something for formal groups, not for elliptic curves, but it's a very formal construction. I could replace the formal group with the curve, and then I with a suitable sheaf, the ideal sheaf. And so the fact is that elliptic curve C has a unique cubical structure in. So if you take the unique cubical structure in an elliptic curve, and if you have an elliptic spectrum, that automatically gives you a cubical structure on its formal group, because the formal group of the spectrum is the completion of the elliptic curve. That's what an elliptic spectrum means. So theorem 1, should move it up. Theorem 1 says that, so mu bracket 6 is the thing corresponding to cubical structures. Theorem 1 says that every elliptic spectrum has a canonical map, ring spectrum map from mu bracket 6. Theorem 2 says that if you have a Moravi-E theory that carries a structure of elliptic spectrum, it has a canonical H infinity map from mu bracket 6. So this orientation for mu bracket 6 is a somewhat weaker version of the Witten orientation. In fact, if you want to write down the cubical structure for the formal group of an elliptic curve, a way you can do it is to use the Weierstrass sigma function, which is precisely the thing that defines that constructs the Witten orientation in its most classical formulation. So I think I'll just stop with that discussion. Well, I'll say one more thing. So the second half of this talk, in the original plan, which I knew I was going to ditch, but was going to be, I was going to talk about the Ando-Hopkins-Rezk construction of the actual orientation. The only thing I want to say about it is that proof is very different than this. It's in fact not clear what the relationship between this is, not clear to me at least. Not my co-authors might have other views, but I can't figure out what the relation between this theory is and the proof that we actually came up with. The proof that, this isn't really good enough to construct an orientation for TMF for several reasons. First of all, it's BU6 and not M string. You can't really do this for M string. It's not an even space, so it's necessarily more complicated. This works for Moravi-E theory. You can do this for some other, localized, commutative S algebras, which are even periodic. And so you might hope to be able to construct a map to some inverse limit of such things once you have this, but you kind of sort of start losing control. But one of the first problems that you lose control is that you don't actually get a map of commutative S algebras. You just get an H infinity map. So the very first thing you have to do is you have to refine your H infinity map to an actual commutative S algebra structure. They thought about how to do that a lot, but it's extra work. And so that plus the fact that you're not really working with M string, that means it's very hard to turn this into a proof for the theorem you actually wanted. And so our other proof uses has input, some additional input that somehow isn't in this story, like the stable atoms conjecture and something called the Bausfield-Kuhn functor. That doesn't go into this story at all. But I find this is sort of a very beautiful story, and I just wanted to make this, even though it doesn't prove the theorem you want. I mean, there's something here about this. Oh, and the other thing I didn't talk about was another facet of the Witten orientation, which is rigidity. I'll just say this. I'll refer you to papers, first of Ionid Rosu, and then various papers of Matt Ando with collaborators. There's an equivariant aspect to the Witten genus, which people first understood in terms of the property called rigidity. And it turns that story can also be explained in terms of this cubical structure. The cubical structure, after all, lives over the elliptic curve. In the story, there's a derived elliptic curve, or at least a cohomology thing that takes values in sheaves on an elliptic curve. And you can show for suitable bundles the associated the cohomology of the tome spaces of some equivariant bundles with the right characteristic classes. Those give rise to sheaves on the universal curve, and you can produce sections for those sheaves in certain cases. And that's precisely an equivariant version of this story. It's built from the same idea that you have this cubical structure to work with. So I'll just point you in that direction. So next time I'm going to talk about an aspect of the AHR story that does involve power operations, which has to do with something called the logarithmic operation. So that's what I'll talk about next time.